Okay, and continuing on with systems of differential equations, we now have those systems with initial conditions. And for what we have from page 378, okay, we have these two equations where we have the first order derivative of x01 of t is equal to 3 times x01 plus 4 times x of 2. And we have the first order derivative of x of 2 of t is equal to 3 times x of 1 plus 2 times x of 2. And we have, with the initial conditions, at t is equal to 0, we have both x of 1 and x of 2 set equal to 1. And now starting out with what we have from the vantage point of finding out the general solutions and then using the initial conditions to find out the specific solutions for x of 1 and x of 2 that will fit into both of these differential equations. Again, we can start out with the coefficient matrix. Okay, so we have A is equal to, and we have for the matrix, again, we have the 2 by 2 arrangement. First column we have with the x of 1 coefficients. Second column we have with the x of 2 coefficients. And once again, we had the utilization of the identity matrix. Again, so you have 1, 0 and 0, 1. And once again, creating the pathway to determining the eigenvalues. Okay, so we have, again, the determinant of A minus lambda I is equal to 0. And for what we have in the determinant setup, okay, so just mapping together, so we have 3 minus lambda times 1, so we have 3 minus lambda. And we have 4 minus lambda times 0, so that stays at 4. We have 3 minus lambda times 0, so we have 3. And we have 2 minus lambda times 1, so we have 2 minus lambda. And we have equal to 0. And again, just taking the products. Okay, so working diagonally. Okay, we have 3 minus lambda quantity times the quantity of 2 minus lambda. And we have minus the product of the diagonal that runs from the lower left, to the upper right. So you have minus 3 times 4 is equal to 0. And once we multiply out and combine like terms together, so we're going to have lambda squared minus 5 lambda minus 6 is equal to 0. And we have, upon factoring, so we have lambda minus 6 quantity times the quantity of lambda plus 1 is equal to 0. And applying the zero product property, okay, if we let lambda minus 6 be the first, we have that lambda 1 is equal to 6, and that lambda 2 is equal to negative 1. Now, in the crossover to determining, okay, the eigenvectors, again, so we have the matrix, whereupon we have A minus lambda I. We have times the eigenvector, okay, is equal to 0. And taking what we have now, okay, so we just have conceptually, okay, let me just mention, okay, so if I have A minus lambda 1 I times the first eigenvector equal to 0, okay, so we had the first eigenvalue at 6, okay, so we have for lambda 1 equal to 6. Okay, so just filling in. So if you go back to the determinant setup, so you have with lambda equal to 6, you have 3 minus 6, so this will be at negative 3. 4, you have 3, and 2 minus 6, so this will be at negative 4. And we have with the first eigenvector, okay, so we just designate the coefficients A of 1 and B of 1. And the matrix setup we have for this system representing 0, so we have a 2x1 matrix that will have only 0 as the constant. Okay, and setting up what we have here, and you can map either -3 with A of 1 simultaneous with 4 and B of 1, or you could do 3A1 minus 4B1. Either way will be fine. So we have, let's say we have -3A1 plus 4B1 is equal to 0. And in effect, we have 4 times B of 1 is equal to 3 times A of 1. So for what we will have in this particular regard, okay, is that for the first eigenvector, okay, so we have consisting of A of 1 and B of 1. Okay, so you have 3 times A of 1 is equal to 4 times B of 1. So A of 1 is going to be higher than B of 1. And we'll say that maintaining a 4:3 ratio, okay, we have like 3 times 4 is equal to 4 times 3. So we say that A of 1 is equal to 4 and B of 1 is equal to 3. So we'll just say that for the first eigenvector. Okay, we have 4 and 3. Now, so this is what we have for the first eigenvector. And if I were to work with the determination of the second eigenvector, okay, so I have again the second eigenvalue. We have a -1. And so we're now going to have, okay, so you have 3 minus -1. So that's going to be 4 and 4, and we have 3. And we have 2 minus -1, which will be at 3. And we'll have for the 2x1 matrix representing V of 2, we have A of 2, B of 2. And again, we have equal to 0. Okay, and again, you can do the bottom or the top. And we'll just say we have for A of 2 plus 4 times B of 2 is equal to 0. So we have 4 times B of 2 is equal to 4 times A of 2, or in this case, -4 times A of 2. So we have 4 times B of 2 is equal to -4 times A of 2. And I can just lower this saying that there is an additive inverse relation between A of 2 and B of 2. And now, for the second eigenvector, okay, so you have A of 2 and B of 2. And you can have 1 at the top, -1 at the bottom, or vice versa. So we'll just say that we have, we'll just let A of 2 be -1 and B of 2 be +1, but it could be the other way around. All right, now in crossing over to what we have for the general solution, and then we'll get to the specific. Okay, so we have for x, so you have is equal to a constant times the eigenvector times e to the product of the eigenvalue times t. Now, we have a 2-equation system, and for what we're going to have in the mix, okay, so we have C of 1 times V of 1 times e to the lambda 1 times t plus C of 2, V of 2 times e to the lambda 2 of t. All right, so you have C of 1. And again, we had with the first eigenvector. Okay, so you have 4 and 3. And we have e to the 6t. And we have plus C of 2. And for V of 2, I have -1 and 1. I have times e to the negative t. So for what we have for the first general solution, so we have x01 of t. So we have 4c01 e to the 6t minus c2 times e to the negative t. And for x02 of t, we have 3c1 e to the 6t plus c2 times e to the negative t. And utilizing what we have for the initial conditions. Okay, so you have x1 naught and x2 naught. We have each equal to 1. And referencing what we have from the general solution. Okay, so you have x1 naught, so you have 1 is equal to, and we have 4 times c1, and e to the 0 goes to 1. We have minus c2, and we have x2 not equal to 1, and we have 3c1 plus c2. And we can utilize the addition method. Okay, so we just have the negative and the positive c2 to cancel out. If we add these equations together, so we have 2 is equal to 7 times c01. And so we have c01 is equal to 2/7. And if I plug 2/7 back in, it's going to follow that for what we have in the case of CO2. Okay, that is going to be equal to 1/7. Okay, and so what's going to happen in effect is that for what we have for x01 of t, okay, so you have 4 times c01, so you have 4 times 2/7 times e to the 6t. We have minus 1/7 of e to the negative t. And for x02 of t, okay, so you have 3 times c01, so you have 3 times 2/7 times e to the 6t, and we have plus 1/7 times e to the negative t. And so it's going to follow that one solution that we have in the system. Okay, so we have for x01 of t. So this will come out to 8/7 of e to the 6t minus 1/7 of e to the negative t. And for x02 of t, okay, so you have 6/7 of e to the 6t plus 1/7 of e to the negative t. And that will be the result for what we have in this system.